This lecture we'll discuss Bernoulli's equation, we'll derive it, and talk about some of its implications. But first we need to discuss some things I forgot in the last lecture. So first, I was discussing density and water, and I mentioned that water, unlike air, the density is pretty much constant. With air you can compress it and increase the density. With water, I said the density is pretty much constant because you can compress it and increase the density somewhat. You can also affect water's density by changing its temperature. So as you cool water down, the density increases somewhat, and that's why cooler water will sink to the bottom of a pool or a cup or whatever it may be. This is true down to about 4 degrees Celsius, and below that temperature, water actually starts to expand again. So if a lake is all below 4 degrees Celsius, then actually the warmer water will be on the bottom and the cooler water will be on the top. And this is why lakes always freeze from the top, or a cup of water, if you stick it in the freezer, it will start freezing from the top. And it's also why the bottom of the ocean tends to all be about 4 degrees Celsius, because 4 degrees Celsius water is the densest kind of water. So I just want to mention those facts about water and the slight variations in its density due both to pressure and temperature. But again, these are slight variations. It's nothing like a gas where you have much greater variations. A second thing I forgot to mention was, in the context of pressure, I wanted to talk about the work done by a gas. So if we have some gas, let's say existing in a cylinder, and a sort of piston that can be pushed in this way, and let's say that this piston has some area A, and this is going to compress the gas which lives in here. We could ask, what is the work done on the gas? So let's suppose that the piston is pushed in some distance delta x. The work done on the gas is, of course, equal to the force times delta x, as always. And we can note here that the force is equal to the pressure of the gas times the area of that piston. That's the force exerted by the gas on that piston. And this quantity, area times delta x, well, that is just the change in volume of the gas as we push that piston in. So this is change in volume. So that the work done on the gas is pressure times delta volume. Work done on a gas is PdV. We should really put a minus sign here because the density of the gas is decreasing. So work done on a gas is minus P times the change in volume of the gas. Work done by the gas is plus P times the change in volume of the gas. So a gas expanding is doing work. That's actually why it cools down, because in order to do work it has to use some of its thermal energy. Okay, so work done by a gas. We'll actually use that in the derivation of Bernoulli's equation. One third thing I wanted to mention that I forgot had to do with continuity. I described it as conservation of volume, or conservation of amount of fluid. Now this is a good description when dealing with fluids like water, where the volume does not change substantially. But if the volume of a fluid can change, such as when we're dealing with air, then of course volume is not conserved, and we should think instead of continuity as conservation of mass of fluid. So it's conservation of mass or that is the same as conservation of volume for an incompressible fluid flow. Now, incompressible fluids could be of course water, but also air. If the pressure is not changing very much, then it effectively behaves as an incompressible fluid. Okay, so having gotten those things discussed, let's talk about Bernoulli's equation. We'll start by deriving it, because Bernoulli's equation can be derived from conservation of momentum. Conservation of energy. It's essentially just an application of conservation of momentum. Once again, conservation of energy to fluids. So suppose we have some pipe through which some fluid is flowing. Could be a pipe of changing cross-sectional area, we want to consider applying conservation of energy to the fluid in this pipe as it moves on this side some distance delta x. Over on this side, the skinnier side, due to continuity, is going to move a larger distance delta x because so we could call this delta x2 and delta x1. And delta x2 has to be larger because these, the change in volume on both sides has to be the same. Okay, in other words, what we should say is V2 and V1 must be equal, where V1 is the amount of volume of fluid pushed into one side of this pipe, and V2 is the amount that comes out the other side. So let's apply conservation of energy. The initial energy, or really what we should calculate is the change in energy, and the change in energy must be 0. So delta E, which is going to be 0. Let's see, there is going to be some velocity of the fluid here at the bottom of the pipe, and some velocity of the fluid at the other end of the pipe, so we'll call these V1 and V2. And as we move the fluid up the pipe, we have more fluid now up here going at a velocity V1, so there's some kinetic energy associated with that. At a velocity V2, and we have less fluid moving at a velocity V1, so 1/2 mv2 squared minus 1/2 mv1 squared. All right, as we cram fluid in this side of the pipe, it has to go faster coming out here, and that results in an increase in velocity, increase in kinetic energy, so there's the change in kinetic energy. There's also a change in gravitational potential energy, because this end of the pipe is higher. So we'll call this height h2, and we'll call this height h1. We could call this delta h if we want, but I'm not going to use the symbol delta h right now. So we'll have mgh2, new gravitational potential energy at the top, and minus mgh1, for the gravitational potential energy lost as we have pushed fluid from here up to here. And so if you're, you may notice that this is just mg delta h, but I'm going to leave it in this form because it's going to make it a little bit easier to write the Bernoulli's equation. And so what other changes in energy do we have? Well, we have some work done on the fluid, and that is going to be pressure times change in volume. Now up here the volume is increasing, or basically the fluid is doing positive work because it is pushing out. So that means that a negative work is being done on the fluid. Down at the bottom we have a positive work being done on the fluid. Right, okay, here's really the way we should think of this. This change in energy, it's not going to be zero. It's going to be equal to the total work done. And once again, up at the top, we have a positive work done by the fluid. That's equal to pressure up at the top. So we'll call the pressure here pressure 2. And down here, we'll have pressure 1. So we have a negative work done on the fluid minus P2 times the volume, and at the bottom we have a positive work done on the fluid, so that's plus P1V. Okay. At this point, let's use the definition of density. This is 1/2. The mass of fluid is equal to the density times the volume, V2 squared, minus 1/2 rho volume V1 squared. Excuse my handwriting. Rho volume G H2 minus rho volume GH1, and by now you may be seeing where this is going. Minus pressure 2 volume plus pressure 1 volume. We've got a volume in every term here, so let's cancel them each out. That one, that one, that one, that one, that one, that one. Great. Now I'm going to put everything with a 2 subscript over on the right side of the equation, and everything with a 1 subscript over on the left side of the equation, and basically we're going to get P1 plus rho G H1 plus 1/2 rho V squared, V1 squared, equals P2 plus rho GH2 plus 1/2 rho V2 squared. So let's put a box around this, even though it wound up at the bottom of the screen. This is really important, well worthy of a box, and oh god, what have I done? Zoom, let's see, view, zoom, not zoom, 200%, but 100%, I don't even know how I did that. This is Bernoulli's equation. It's just conservation of energy applied to a fluid, and then we take the volume out. You take conservation of energy and divide both sides by volume, and this is what you get. Sometimes it's also written, for example, it's written this way in the book, as just pressure plus rho GH plus 1/2 rho V squared equals a constant. Okay, now one thing I should note about Bernoulli's equation is that I've completely ignored any kind of anything like friction in the fluid. Now there is something like friction in a fluid. It's called viscosity, and you can, when you stir up a fluid, some of that energy can be turned into heat. So Bernoulli's equation is ignoring any viscosity of the fluid. Okay, let's look at some implications of this, and we will, I'll blank the screen, so pause now if you're still studying any of this. All right. Okay, so implications of Bernoulli's equation. First we have, let's say, speed of some fluid leaving a bucket with a hole in it. Here's a bucket. It's got a nice handle. Okay. And let's say it's one of those little giant like drink coolers full of Gatorade. And we'd like to know, what is the velocity at which fluid comes out of this thing? Well, we can determine this using Bernoulli's equation. Now, in conservation of energy, we would usually pick some initial state and a final state. In Bernoulli's equation, we pick not a state, but a position. And let's call this position 1, and this position will be 2. Bernoulli's equation says that pressure at 1 plus rho GH1 plus 1/2 rho, I'm going to fix that 1 so it does not look like an L, 1/2 rho V squared equals pressure 2 plus rho GH2 plus 1/2 rho V2 squared. Okay, so what do we know about these things? Well, first of all, what is the pressure at 1? We are at, it's exposed to the atmosphere. Okay, there might be a lid, but it's not an airtight lid, so basically the pressure up at the top surface of this liquid is the atmospheric pressure. We'll call that P naught. What about the height? Let's call that rho G D. D will be the depth of the fluid in this cooler. And what about the velocity up here? It's basically 0. Now, it's not exactly 0 because, of course, as liquid comes out of this spout, the surface will drop down, but it drops down very slowly, and that has to do with the fact that there's a very small area here and a very large area here. So continuity equation is going to say that whatever the velocity is here, the velocity here is much, much less. And so that means basically we can neglect the kinetic energy term for the fluid for the surface of the fluid slowly coming down. It's just so slow that it's very small. Okay, what about on the other side of the spout? Well, that's also exposed to the atmosphere, so the pressure there is also atmospheric pressure. Okay, let's define, recall that in conservation of energy, and it's true in Bernoulli's equation, that you can define what your H equals 0 is. What is 0 height? As long as you're consistent about that throughout. So we said that the height at the surface was D, the depth, so the height at the bottom of the bucket then is in accordance with that convention, it's 0. Now you might say, okay, is the spigot quite at the bottom? There's maybe a little distance there, but it's small, so we're okay ignoring it. So basically the height there at the spigot is 0. 0 relative to, by the definition we've established that this is 0 height and this is a height of D, the depth of the liquid inside. So what is the kinetic energy term? 1/2 rho V2 squared. Well, that's the thing that we're looking for. Okay, the atmospheric pressure cancels out on both sides of the equal sign, and what this leaves us with is rho G D equals 1/2 rho V2 squared. We can solve for V2, and I'm just going to call it v because there's only one velocity in the problem now, and we get square root. Okay, by the way, note the rows cancel. Square root 2gh. Whoops, I'm calling it d. But when I write an h there, it almost is more evocative of something that might be familiar. When we first applied conservation of energy to like a sledder sliding down a hill frictionlessly, we found that their velocity at the bottom of the hill was square root 2gh. It's the same answer, no surprise. It's the same underlying physical phenomenon. It's conservation of energy that allows us to determine the velocity of water exiting this drink holder. So that's one consequence of Bernoulli's equation. We could call this sort of speed of fluid egress. Okay, pause if you're studying this. I'm going to blank it. And we're going to turn now to another consequence of Bernoulli's equation. And this phenomenon is sometimes called pressure head. And the question here is, and by the way, each of these phenomena are also, in a way, small sample problems. So the question here is, what is the water pressure at your house? Okay, you've got a sink. Here's the sink. Here's like the faucets. And water's going to come out of the faucet. And what is the water pressure? When the faucet is off, under what pressure is the water inside your faucet? And it's nice to have a high water pressure, because then, like, you get like your shower head and your garden hose, they all spray farther, and helps you rinse off your dishes or whatever it may be. So what is the pressure there? Well, this is connected via a bunch of plumbing to, depending on where you live, it may be connected to a giant water tower. Okay, so here's a water tower, and that's connected via some plumbing to your sink and to all the other houses. And there's some water filled, the water tower is filled up to a certain height. So let's apply Bernoulli's equation. This will be the location 1, will be the surface of the water here, and location 2 will be, I've already implied it by using the subscript there, 2, on the pressure 2. Location 2 is inside your plumbing, right at your sink. Okay? What does Bernoulli's equation say? So let's write down Bernoulli's equation. I'll write 2 on the left side since it's on the left side of my drawing. Rho GH2 plus 1/2 rho V2 squared equals pressure 1 plus rho GH1 plus 1/2 rho V1 squared. Okay. What is pressure 2? Now, first thing to note here is that pressure 2, it actually is cut off from the atmosphere. When your sink is off, okay, the inside of the pipes are holding a certain amount of water pressure, and as long as your seal is good, then the water pressure there is going to be much higher than atmospheric pressure, and that's ultimately the thing we're trying to solve for. So we can't call this atmospheric pressure. If the sink was running, we could say it was atmospheric pressure just outside the sink. But inside your plumbing, it's not at atmospheric pressure. It's at a higher pressure. We're trying to determine what that pressure is. Okay, the sink is on the ground, or it's pretty close to the ground, so this entire term is just 0. Close to the ground, at least compared to the height of a typical water tower. The sink is off, so water is not flowing. So this term is also 0. Up here, the water tower, not a watertight thing. This is exposed to atmospheric pressure. So this is P0, atmospheric pressure. And the height then will just be the height of the water tower above the ground, rho GH. And again, water is not flowing right now, the sink is off, so this term just disappears. So on the left side, all this left is P2, and it's equal to the atmospheric pressure plus rho GH. Now, when considering water pressure and how fast it's going to come out of a sink, what we're really interested in is the differential pressure. In other words, how much greater is the water pressure than the atmospheric pressure, and that's equal to just rho GH. Okay. This is sometimes also called hydrostatic pressure. Hydro, the prefix, think water, and static, think not moving. So this is the pressure caused by water when it's not moving. Now I just want to take a moment to note here, a totally different question that we could have asked is, when I turn on the sink, what is the velocity of the water coming out of the sink? Now, for that would be essentially exactly the same as the previous question, and we would get the velocity of the water coming out of the sink equals square root 2gh. So I just wanted to note that as another kind of context in which that equation applies. That was supposed to look like a cloud, but it looks like a, well, I'm not sure what it looks like, but pretend it's a cloud. Okay, so pressure head, that's a phrase typically assigned to this like plumbing problem of like how high above your sink is your water coming from and how much water pressure do you have because of that. Hydrostatic pressure is a more general term for the pressure due to basically it's pressure due to the weight of the water. It's the weight of all this water trying to come and push water out of your sink. Okay. Pause if you're still studying this. I'm going to blank it. So suppose you're a diver. Okay, similar stuff. Here's somebody diving. You've got some like air tank on, and hose and goggles. It's really hard for me to draw on this with this stylus, but I'll probably get used to it eventually. And you've got some flippers. And you want to know, what is the pressure? Well, it's exactly the same problem as we just did. The pressure below the water is equal to the atmospheric pressure plus rho g times your depth. How high above the surface of the water? How high above you is the surface of the water? Okay, so there's this phenomenon of hydrostatic pressure manifesting itself again for divers. Let's see, so that's another application of Bernoulli's equation. We can do, sometimes this is called dynamic pressure. Basically the velocity of some fluid influences pressure. So let's consider a physical situation where we can see dynamic pressure manifest itself. One example is if you've got let's see, actually what we should do is we should do like a mercury hygrometer before we go into dynamic pressure. This is another hydrostatic pressure thing. If we have a bowl of fluid, and as I already hinted at, it's going to wind up being a bowl of mercury. Be careful. But more generally, it's just going to be a bowl of fluid. And we've got some kind of upside down kind of glass tube here with vacuum inside it. In other words, zero pressure. It's going to pull up, it's going to suck up some of that fluid, some height above the surface of the fluid in the bowl. So why does this happen and what does it mean? Well, once again, Bernoulli's equation. Okay, inside this tube we have zero pressure. Okay, the gravitational potential energy term is rho gh. Kinetic term is zero. Outside the tube, we're going to have atmospheric pressure. Now the potential energy term is zero because we're at a height. We'll define this as zero. This is height h. Again, flow, nothing, no flow going on, everything's sitting still, so the kinetic term is zero. And we've got atmospheric pressure is equal to rho gh. So, you can use a device such as this to measure the atmospheric pressure, and traditionally mercury is used. And for that reason, pressure, it gives another unit of pressure, which is the millimeters of mercury. Where basically when you're measuring pressure in millimeters of mercury, you're basically saying the atmospheric pressure pushes the mercury up this tube with a vacuum in it. How much does, how far up does it push it in millimeters? And that's the pressure measured in millimeters of mercury. Now you have to use the density of mercury there. I don't know what it is off the top of my head, but it's not the same as the density of water. No reason in principle you couldn't measure temperature, pressure using millimeters of water, just not a conventional thing to do. No one really uses mercury to measure pressure anymore because that's dangerous. Mercury, dangerous. Okay. Just another application of static pressure. What else can we do? Dynamic pressure, right. So one example of dynamic pressure, if you've got say like a drink, a soda, big soda, and a straw. And there's some wind going across it. At some velocity v, across just the top of the straw. Okay, down here there's no velocity. Say the drink is well below the sides of the cup, so there's not much airflow down here. Basically, that movement creates a low pressure that will suck the fluid up the straw a little bit. So let's study this with Bernoulli's equation. At the top of the straw, say we've got some pressure unknown plus a kinetic term, 1/2 rho v squared, and this is equal to down here at the surface of the fluid atmospheric pressure. So by increasing this velocity, we actually create a different pressure inside the straw. Now, I should be clear that here, this is the pressure of the air. Sorry, the density of the air, because this is a movement of air up here. But it creates a difference in pressure inside the straw and outside the straw at the surface of the drink where there's not much flow of air. We can now apply Bernoulli's equation separately to the fluid, which may as well be water, maybe it's soda. So at the top of the straw, there is this same pressure that we have up here, okay? Because at this surface, whatever the air pressure is, that's what the water pressure is. At this surface, the pressures are the same, because it's the same location in space. And this is going to be, let's call this little height H. My handwriting's terrible with this, but somehow I feel like I'm making really good curly braces. So, I don't know, I gotta savor the small victories, I guess. So, in the straw, pressure is P. We're a little bit higher. And the fluid in the straw is not flowing. It's the air up here, well, that's also a fluid. So the water, the liquid in the straw is not flowing. It's the air up here that was flowing that was this velocity. It's in the drink, it's the fluid is not flowing. So there's no kinetic part here. And this is equal to, at the surface of the water, we have just atmospheric pressure, 0 height, 0 flow velocity. So we can, by putting these two equations together, and this is now rho water, what you'll notice is that we can now get that 1/2 rho v squared, couple of, and this is rho air, couple of algebraic steps, equals rho water g times h. So if you ever have a big cup of soda or water and a straw in it, and you blow across the top of the straw, you can determine the velocity at which you are expelling air out of your mouth as you blow across the top of the straw. I've never actually tried this, but I've heard that it works. So this is an example of dynamic pressure, where the flow of air, velocity, and it could be any fluid, in this case we're talking about air, actually results in a change in the pressure. In this case, it's a decrease in the pressure, because on the left side of Bernoulli's equation, we have the kinetic term and the pressure term. So as this goes up, as velocity goes up, pressure goes down. So moving fluids tends to lower the pressure exerted by the fluids. And so we're able to see that using Bernoulli's equation. Separately, we used essentially hydrostatic pressure, which is just another application of Bernoulli's equation, to determine how much that difference in pressure would lift up the water up the straw. And this is the result that we get. Okay. So herein lies another sample problem that could be given. Let's see. I'm going to blank this. We'll talk about another example of dynamic pressure, which is airplane wings and lift. An airplane wing typically has a shape something like, that's a terrible airplane wing, a curved surface on the top, and a flat, or at least less curved surface on the bottom. And this I'm going to try to do even better. Usually have more of a rounded front. Oh my god. I should have kept the one I had before. Yeah, I'm going back to the one I had before. Let me try that again. Okay. That's good enough. So basically, as air flows over the top of the wing, it has to flow at a greater distance than air flowing under the bottom of the wing, because it has to follow this curved path. And that means that it has to go a little bit faster. So if we call this distance something like L top, and this distance something like L bottom, then V top over V bottom is going to be equal to L top over, be consistent about my notation, L bottom. And so if L top is greater, that means V top is greater, and as we just learned from dynamic pressure, Bernoulli's equation tells us that that is going to make less pressure at the top than at the bottom. So pressure top is going to be, we should say, proportional to well, let's see. What's going to be the best way to do this? What is going to be the best way to do this? Pressure top is going to be, pressure top is going to be proportional to velocity top squared. And pressure bottom is going to be proportional to velocity bottom squared. So this is not simple. Essentially, there's going to be a reduction in the pressure at the top, which is going to be equal to, this is going to be a more clear way to explain it, just like last time, and a reduction in the pressure at the bottom, which is going to be equal to 1/2 rho V bottom squared. And so the difference, let's call it, and there's a minus sign on both of these, because higher velocity lowers the pressure. And the difference, P bottom minus P top, is then 1/2 rho velocity top squared minus velocity bottom squared. And velocity top squared, using this expression up here, is going to be velocity bottom squared L top squared L bottom squared minus V bottom squared. We can factor out the V bottom, 1/2 rho V bottom squared L top squared over L bottom squared minus 1. Now, if we want to compute the force, the lift force exerted on the wing, that's going to be the difference between the pressure at the bottom and the pressure at the top times the area of the wing. So there's the area, and then we multiply by, again, the difference between the pressure at the bottom and the top, 1/2 rho V bottom squared, times these geometric facts involving the wing, L top squared over L bottom squared minus 1. So the way this result is usually written is as a proportionality relationship. In other words, we just call this some constant, right? Let's call it c, and the lift is equal to a constant c times the area. Let's absorb the 1/2 into that constant as well, times the density of the air times the velocity squared through which the wing is moving through the air. And this is called the lift equation. Yet another consequence of Bernoulli's equation, that the lift force on an airplane wing is proportional to the area. So more area, that means more lift. The density of the air, so as you get up into higher altitudes, you get less and less lift because the density is decreasing. And it goes like velocity squared. So if you double your velocity, you quadruple your lift in this simple model of lift. Now the lift equation, by the way, applies not only to airplane wings, but also to propellers on an airplane, because it's the same basic operating principle that allows a propeller to drive an airplane forward. Also rotors on a helicopter and sails on a sailboat all use a similar operating principle. And so the lift equation can be applied to, in principle, all of those different contexts. So yet another consequence of the Bernoulli equation. Okay, what else? We're not done. The Bernoulli equation does so much awesome stuff. So, what we'll do next? Let's do buoyancy. Okay, we've talked about hydrostatic pressure. Let's consider now some water and an object like maybe a cube. Submerged in the water, and this object is going to have some height and some area at the top and the bottom surface. Note, by the way, that its volume is then equal to its height times its area. Now, let's consider the hydrostatic pressures exerted on this object. There's going to be hydrostatic pressure pushing up from underneath, and there's going to be hydrostatic pressure pushing down from above. There's also going to be hydrostatic pressure pushing in from all sides. But here's the thing. The pressure from the left and right side are going to cancel each other exactly. The pressure on the front and back, they're going to cancel each other exactly. The pressure on the bottom and top are not going to cancel exactly because the pressure at the bottom is greater because it's deeper in the water, so there's more hydrostatic pressure. Okay, so if we want to consider the net force exerted on the object by the fluid in which it's immersed, right? And we'll see it's because this is eventually going to be called buoyant force that I'm calling this FB. That's going to be pressure top times area, and that is a downward force plus pressure bottom times area. And the difference in these pressures, so this is going to be area times pressure top is basically well, so the difference in these pressures is going to be just due to hydrostatic pressure, rho g, rho g times the difference in their heights, because the difference in pressure is purely just hydrostatic pressure, and hydrostatic pressure is rho g h, and so h is the difference, is the height of the object, so that's the difference in the height between the top and the bottom. So note now that we have rho ah g. Well, ah, remember that's volume, so this is rho v g. So that is the buoyant force. buoyant force, buoyant force is another word, by the way, for like the flotation force, the thing that's making this thing try to float up above the water, is equal to rho times volume times g. Now, note, this is rho of the water, or the fluid in which the object is immersed, okay, because that's the hydrostatic pressure is rho gh, and that's the rho of the fluid, not of the object. Now, sometimes this is written as just rho times volume is, of course, mass. So sometimes this is called mass displaced, and be careful, because it is not. This is a useful form of the equation here, though, so I'm going to put a box around that. It is not the mass of the object, because this is not the density of the object. It's the mass of fluid that's been displaced, and so don't forget that it's still a g there. Is not the mass of the object, it's the mass of the fluid that's been displaced, because this is the density of the fluid. So it's the density of the fluid, essentially it's the mass of fluid that is pushed out of the way to make room for this object. So that mass times g is, of course, weight. So sometimes it's said that just buoyant force is the weight of the fluid that's been displaced by the object. Okay, this whole thing, this is called Archimedes' principle. Archimedes' principle, or Archimedes' law. I'm going to call it Archimedes' law. And basically, that is not my best parenthesis. It's basically spelling buoyant, B-U-O-Y, buoyant force. So buoyant force is equal to rho times V times G, or the weight of the fluid that's displaced by the object. That weight gives you the buoyant or the flotation force that is pushing it upward toward the surface of the liquid. Okay. One more thing, really. One more important consequence of Bernoulli's equation. Bernoulli's equation it does so much awesome stuff. So I'm going to blank this, pause it if you're still studying. And basically, if you've just got some fluid, this one's pretty easy. Alright, here's 1, here's 2. Bernoulli's equation says pressure 1 plus rho g h1 plus 1/2 rho v squared equals pressure 2, v1 squared, 1 plus rho g h2 plus 1/2 rho v2 squared. If you increase pressure, say over at 2, and you don't change height or velocity or anything, there's going to be a corresponding increase in the pressure over at 1 to satisfy Bernoulli's equation. So if you sort of increase the pressure in a fluid somewhere, you increase the pressure in the fluid everywhere. And this fact is called Pascal's principle. Okay. All right. That's it for this lecture. We're going to recap now, because there was a lot in this lecture. And there was a lot in this lecture because Bernoulli's equation is just so awesome and does so much. Okay, so we had Bernoulli's. And from Bernoulli's, what on earth did we derive? We derived this thing, hydrostatic pressure. Hydrostatic pressure. We derived this phenomenon of pressure head, what gives you your water pressure. Y Why are water towers, these giant towers, way up in the air? So that you have some some water pressure in your house. So hydrostatic pressure was like basically delta P equals rho G, difference in height. Pressure head was almost just the same thing. Pressure at your faucet is rho G times the height of the water tower. We had speed of egress, rate at which fluid leaves a bucket or something like that, and that was velocity equals square root 2gh. We had dynamic pressure, and that was delta P equals minus 1/2 rho V squared. We had, what else did we have? I can't even remember it all. We have buoyant force, buoyant, B-U-O-Y-A-N-T, force, and that was force buoyant equals rho volume times G, and that is rho of water or whatever fluid is that you're immersed in, and this is sometimes just called weight displaced. Remember, weight of the fluid displaced. And then we have Pascal's principle. Which just says you increase fluid one place, you increase fluid another place. So Bernoulli's equation, so many different really important consequences. And oftentimes all these different things are taught as like separate laws. Pascal's principle, buoyant force, hydrostatic pressure, dynamic pressure, but they're all one law. They're all just Bernoulli's equation. And so I'm always trying to emphasize this in this class. You don't actually have to remember any of those things. You just have to remember Bernoulli's equation, because from Bernoulli's equation you can derive any of those things from the things that we've just gone over now. And do you actually have to remember Bernoulli's equation? No, because Bernoulli's equation followed from conservation of energy. So you just have to remember conservation of energy. And of course, when we introduced conservation of energy, we showed that the conservation of energy actually follows from Newton's laws. So, all of this is just a consequence of Newton's laws. You can see how all of physics, it reduces down to a small number of very, very simple laws. Newton's laws, from that we derived conservation of energy, and from conservation of energy we derived Bernoulli's equation, and from Bernoulli's equation we derived all of these different phenomena. Okay. Good. In the next lecture, we'll do some more sort of complicated and interesting problem solving with Bernoulli's equation.